Go ahead, Mohammed.
Yep. Just a second, two screens are okay. Do you see the screen?
Yes.
So just at a high level, first, thank you very much for making the time to join. And I will actually be very informal about it here. I will reuse as much information as possible from what's available out there. And also, I wanted to maybe I will share a couple of cases where live with a simulation. So the general outline is I'm going to just to get a talk about it in general, and then talk specifically about SPICE, the convergence issues, the DC convergence issues, and then we'll extend that to the multiple operating point circuits and the startup circuits. Now, I will touch on every one of them very quickly without doing into a very deep design thesis, mostly items that will touch on basically knowing that there is an issue and the methodology to be able to assess it and assess the impact on the circuit. So the first thing I'm going to start with is going to be, I'm going to start from the knowledge-based article that was published earlier. And the intent of that article was to not to solve a specific problem. Let me make it clear again. Oops. Not to solve a specific problem, rather to give a guidance on the different approaches or to detect, to deal with the simulation problems. So in general, the issues can be, as you know, the simulator is trying to solve a matrix. That matrix has mathematical properties. Could be if it has any singularities or it has any anomalies that cannot enable the simulator to arrive to a solution, then you won't converge. And some of these things do not necessarily have to be obvious to stop the simulator from functioning. It could be bad. It's either bad practices in high impedance nodes or some of the unrealistic values of the component values or the design parameters that will stretch the models in an extrapolation, heavy extrapolation, which in the nonlinear cases where you have an exponential increase, you may end up with large numbers that are not realistic. So it's not something that is that the matrix will allow within the parameters of the computer solution, as well as the any variables within the equations itself. So the circuit the circuit topologies I'm just listing here issues. It could be I'm listing a few, but there are many, and I didn't want to go in an inventory list of that, but these are kind of a taste of some of the issues that you will see. And some simulators, most simulators will actually handle some of these with the very explicit errors, like node will have one connection, the DC path to grounds. This is usually the simulator can behave in a way that to overcome this by adding mathematical parameters like shunting the capacitors or creating that path in a way that it allows the matrix to be solved. So these are some of the things that if they exist, it will force a different algorithm or approach inside the simulator. Now, the circuits with multiple operating points are interesting because if you have valid, stable operating points in a circuit, which happens a lot in these reference circuits, depending on what simulation you're running with the simulator, you end up converging in a solution or to a solution that is valid mathematically, but it's not valid physically, or both. It could be valid mathematically and valid physically. And the danger of that is that you will assume that the circuit in simulation works, and in the lab, what you end up with either a different, it's completely dead because it didn't operate. That one of the valid operating points would be like in the zero mode, or a case where it functions at a different voltage or a different operating point that actually sticks there. Now, this is where the startup circuits come in place, and I think in general we are told that when you have these circuits, it's almost like you know that you're going to have these circuits, but that have multiple operating points. But there's not a like a bulletproof answer to identify these operating points unless you act on it and you treat it as with judgment, that you interrogate or identify points in the circuit that have this property. So, and I mentioned the large components, and that if you have unrealistic values of the components, it will actually, whether it's physical values or the large values compared to the component model. So if the models are calibrated in a certain range and using different, and these are, by the way, these are all could be mistakes rather than just intentional design that doesn't work. Of course, having a very fast, unrealistic rise times and fall times. Some of them actually happen in some of the top level circuits with the supply. If you're doing a supply ramp, and the supply ramp is very fast, if you are doing that at a chip level, you will probably, depending on the type of ESD structures, you will trigger a high switching because of an ESD which is sensitive to basically the rise time of the supply, basically as if it's an ESD strike. So you will end up with a large current that forces very steep slope, which require, depending on that current, you may actually, if the circuit is operating right, it's not going to happen as an ESD structure. If the circuit is not operating, you will have a convergence problem. The initial conditions, obviously, this is important. That we tend to assume that the simulator also is if it's starting from the right point, then we're going to land on a safe solution. And some of these, generally speaking, the best way to look at the circuit is to assume that look at it from a perspective in the lab. If you assume that it's a time domain problem, and you would have the supply and the enable signals and the different, if there are clocks or otherwise, you will have sequencing of these signals in a way that is consistent with what the system requires. So this is and there are more, and then actually one of the things that I like in some of the articles that I put in the bottom here, and is although it's not specific to NG Spice, but it's actually, obviously, if you look for the data of the article, it's very old, but you will see that it's a systematic approach for what to look for, okay? And then you start looking at the simulator options and trying them, and they have a sequence and dependency that you need to understand before you apply them to the simulator. So if I go back to the page here, so I'm going to stop here just real quick on the circuit level issues. Are there any questions?
I would have one, if you don't mind.
Could you repeat that, please?
Okay, thanks. You mentioned excessively large values of components and or voltage, current sources, and so on. Would you care to be more specific in this exact case? I can grasp the concept of, you know, what should be made inside an integrated circuit, but since you have given us minimum physical dimensions of resistors, transistors, and so on, are there any maximum physical restrictions by the fab?
So it's, and this is actually, let me I will use a whiteboard just for a second here.
Sure.
So the way you look at it, you have to, you're using a model, and the model, in order to create the model, you will typically, you would have a device with a certain L and W. So let's say you have a character, the people who create the models, they will go and choose on some sort of a test structures. They will have W's and L's and arrays, and then you will end up with points on this curve, on this chart here. They will say, here's that W1, L1, okay? And then you will end up with they choose certain areas, and you say, okay, I'm gonna manufacture these on a wafer and then take it, measure it, and create the transistor model, okay? Fit it to that. Now, and you can see that in most of the foundry technologies, they have the effect of the binning. So they would actually say, I will have, this one is bin 1, and then if you exceed the W certain or the L and certain, you go to a different area, and they characterize it differently. Now, the problem here that happens is that when you're fitting the models, depending on which process and which effect, there probably won't be one fits all. Like if you're trying to fit a certain effect here in a certain range of bias and W, well, you may actually use a part of the model that, but if you want to fit it in a different area, you have to violate this one. So what happens is you start calibrating the models in the binning approach. Now, whether there is binning or not, so in the cases actually specifically when you don't have binning, if the characterization is happening here, and then someone is using the transistor in this, well, here or here. So if this value is reasonable, meaning when I say reasonable here, it doesn't mean it actually depends on the case. But if you're extrapolating too much in a way that where the device wasn't characterized in that space at all, you're subjective either error, you're going to get a larger error, or you get a discontinuity you put the model in a place where there's discontinuity. And this is because it's not designed to handle this. That's at a high level what it is. More about the extrapolation and apply and getting the models in discontinuities to appear, or the exponential nature of the equations to kick in a way that is that doesn't compute.
Okay, but yes, I agree. But my question was: is there an actual maximum allowed size for, say, a resistor from the fab? Like, do they say don't make it larger than this?
So I'll have to say the answer is yes.
Just model dependent. So
the answer is yes, and it depends on the process. So if like I'll tell you, you can see in the processes where the higher voltage processes and the more like let's say 180 and 350. Okay, these types of process, you tend to have if you have a large area of, let's say, a gate area, it would have a different effect there's the maximum is usually judged by the potential for failure. So when you have a larger device that with a very large area, if there is a defect that in any part of that device, it could potentially, it will increases the probability of ruining that device from a yield perspective. Okay.
Okay.
So just, and that becomes a very bad or very common when you go down to processes like 45 nanometer, etc. Actually, just the whole gate oxide integrity effects and the defect density related, they would be, we have to put rules in based on the sizes, just based on the statistics of the process, not because of optics, not because of of anything but the statistics.
But Mohammed, can I interject? I mean, this is definitely true for 45 nanometer, and I know that there are problems as soon as you get below 180.
Mm-hmm.
But I'm not aware of any specific maximum device size specified by XFAB for the 350 process.
Yeah, so I agree with you. That's why I said the answer is yes.
Yeah, there are practical limits, yeah, but no specific limit.
No specific limit. In general, yeah, thank you, Tim. And in general, Alexander, as a design practice, when there is no limit, you always, it's always, you got to be careful, okay? You always, if there's no limit, so the next question is, so what is where do people typically use it? What has been fabricated in the history of this process? If people, if you go back to the previous chart that I had, if most of the designs, and this is something you don't see it, you don't see it until it happens. So yeah. In general, yes, there won't be a maximum, but you have to, I will have to ask myself, like, roughly, what are the people doing? Otherwise, if I am the only one that's going to use the device in that size for the first time, it may work, but it's actually something to be, is there a design methodology? I'm just maybe dividing the device. Maybe if it doesn't impact you, the parasitic effects by adding more of a dividing transistors onto fingers, is that a better thing or not? Okay, so you tend to make the design more robust by making judgments like these if you don't know for sure that it's an open-ended thing. But as Tim said, for the process like 350, no.
Okay, so we are good to go if we try to make a resistor 100 micrometers long. It should be fine.
According to the hard rules, can you confirm that, Tim? There are no rules on that. The rules are like hard rules. I just want to make sure that I'm not speaking for 350 without.
Sorry, I was having trouble finding my window again. But yes, there's no problem with 100 microns. There's a practical limit to the specified area that XFAB gave for this whole thing, which was, I think, 200 by 300 microns for the whole design. So obviously, anything larger than 300 microns is going to fail. But a device that's 300 microns, no, there's no problem with that.
Yeah. Okay. Thanks a lot. You just thanks a lot. I lost my legs for a moment, but now it's fine.
Okay.
Yeah.
Fine.
Sorry. So again, but I have to say that it's always, even outside this challenge, it's always wise to understand or to even get some data, like looking at the devices that are being used, looking at the characterization manual for the process, looking at some of these things to understand what are people doing. And I have personally seen enough of these experiences that when you use that, especially if it's not a hard failures, if it's a failures that are related to accuracy and expectations of certain corner performance, if you're, and again, I'm not saying it's specific to a challenge, this is in general, if you're doing something for the first time, there's a higher risk, right? So it needs some sort of the double checking and some sort of a risk mitigation, if you will, including asking somebody, like when I had a situation like this, I would ask someone who's used it before in a real silicon and say yes or no and get some feeling about it. But yeah, so let's, I don't mean to scare you here in that. Is there any other questions on this topic, in this area? I mean, there's more, obviously. And
thank you.
So now, I'm gonna step into the simulator options, and obviously I'm including the manual here, and the manual is actually has a comprehensive set of options in different ways to treat the equations. Most of the time is that these knobs have to be understood to the level where you need to understand the impact on the circuit performance of or the results. So you're solving a mathematical problem with a certain accuracy. So if any one of these parameters is adjusted in such a way that impacts the solution value, the final value, then that creates a problem or a signal or a red flag that you have for example, if the voltage reference, if I'm changing any one of these tolerances or any of the control, if it changes by a large amount, that means that there is a risk that I'm actually either the circuit is really failing big time, or there is something that I'm doing that's modifying the circuit. So some of the options that we picked here for depending on the analysis you're doing is the AppStall, the Gmin, the real toll, the R shunt, and ITL1 and D and toll. So, and these are, as explained here, they're the absolute tolerance. For example, AppStall is the absolute tolerance value, and there is a default value for that. And if sometimes you cannot converge because you cannot get into within the tolerance value, so relaxing that may help. Okay, but again, relaxing it too much, if you are solving for a value. And it's all about mathematics. If your solution is here, and then there's some sort of a behavior, and you're trying the mathematical iteration is leading you within a certain error margin. If you loosen the tolerance, you're increasing the range at which the solution can be found, which reduces your ability to get an accurate answer. So, and all that is subject to the value, the final value you're trying to solve for. And the accuracy of that value within what resolution, what number do you want to see. So now there are some of these parameters that are not just about accuracy here, like the Gmin, for example, or R shunt. They basically, there is an indirect effect, especially for Gmin. Gmin represents the minimum conductance that can be analyzed. And if you're doing that, if you're changing it, you're basically almost putting a filter on the circuit. So you have to always understand the value ratio between such a Gmin factor and the impedances of the nodes you're looking at. And so you can, changing that value, making it too high, basically you're almost, think about it, you're basically putting a filter on what the simulator cannot do in this. So, and my recommendation in all these cases is that to run multiple values and understand the sensitivity of the circuit to the specific parameter. And real toll is also one of the parameters that apply on both sides of voltage and current, actually, and it has a lot of effect. And I personally did like some sort of a sweep to understand for different problems what the sensitivity of the circuit to changing the relative tolerance. And R shunt adds a resistor to the ground. And if you're doing that, you're effectively modifying the circuit, which creates current that makes the the matrix more solvable from the simulator standpoint. So also it needs to be, if you don't know the values or the impedances of the nodes you're dealing with, the best way to do that is to adjust it in multiple values and see the sensitivity and understand if you don't know it. And in general, there is value that you put it high enough, but it's always important that you understand, either by design or by trying several values, to understand the sensitivity of your original performance to such a parameter. There's a couple of other parameters. One of them actually is the ITL, and you will find it in the manual in different numbers, ITL 1, 2, 3, 4. But this is actually the number of, the ITL in general, it's a limit for the number of iterations that the simulator stops at a certain analysis. So we found that in many cases, if you're telling the simulator, keep going, basically, keep going, don't give up. And so the default value is 100. And if you look at the recommended value we're putting here, we're putting a large value in, and I wouldn't put it in every case, okay? We found that this works if you have a very difficult time getting into this convergence, by putting that value higher, but not excessively higher, because otherwise it can convert into a time problem. So it's important. This is a way to adjust, to speak to the simulator in a way that basically adjusts how many iterations before you give up. And this parameter, it will exist in the manual or different analyses. So if I switch here to the transient analysis, this is the minimal lower limit for the iterations, okay? And they have different values so the ITL3 is not related to the DC operating point or DC solutions. So the different, again, there's no real bulletproof answer across the board. And I believe that a good designer needs to be aware of the limitations and the capabilities of the simulators in a way that they know the blind spots, where they can find an answer and where the simulators cannot give them an answer. I have a general recommendation is that, I'm sorry, I keep using the whiteboard in a way that is very quick, but general recommendation is the analyses. It's either DC, it's either the operating points or running a DC sweep or an AC sweep or AC small signal model. All these things, they're mathematical approaches for us to avoid the transient response and get some different view of the circuit in a way. But the reality is, in any circuit, it always has to start, whatever it is you're going to, if you put a source on a chip, there's a switch you're going to have to turn on. So there's always a transient or some sort of a T starting point, and whether it's a 0 or not, maybe it depends. And then there's a transition that's going to happen for the supply. So if that's the supply will arise when you switch it on. Now, again, depends at what speed and whether depending on the board, the package, and the supply will go up. Now, some circuits, if they intentionally choose, and in one of these cases would be here, is that enabling the circuit would wait until the supply and the system would actually rise in a certain state, and they intentionally want to make it power down state, standby states, where some of the nodes are forced to 0, so you can have completely controlled scenario rather than letting it be alive with the supply. And then you enable maybe, and then you have a signal that would trigger other activities in the circuit. So that's the real world. and it happens this way. Whatever it is that you're doing, it happens so transient tends to be, or it is, the closest formulation or of an experiment that happens in real life. Now, whatever you're doing otherwise, you're trying to understand the transient behavior. So if you have an effect that at the output of a reference and you have some sort of an underdamped oscillation, or it's all about the frequency response of the system, and you're trying to apply either AC analysis or pole zero analysis, or you're doing it with your hand, which is preferred as generally understanding, you will understand the different views for the transient behavior, and that's where so it's always recommended that you try to replicate the transient behavior. And I would not say just recommend it. I would not do it this way. So that's a double negative, but it is that I would always do it in such a way that I can see visible supply behavior with a certain realistic ramp, and basically time domain sequencing. Because the reality is, if you're putting that chip or the IP in a world, there is multiple voltages that wake up at different times, and the sequencing of these voltages is important to avoid leakage or power consumption due to unintended short circuit currents. So in general, I would say transient basically is the key here. Now, and then that brings me to the next point, which is, if one of them is related to the DC, which is the node set, and the other one is the use of the initial conditions. So, but the node, so if I go to the node set, it's actually effectively you're putting a voltage with a source with a resistor, a very low resistor attached to the nodes you're intending to do. And the purpose of that is to try to bring the circuit into a case close to the final solution, and allow the number of iterations to be reduced rather than having it simulated to try many times or many iterations. So you're basically adjusting the window where the solution is happening. And in the transient analysis, you can use the initial conditions, and then in this case, it will actually, if you leave it, usually in the transient analysis, you add UIC. There are examples of that in the manual. And then once you enable that, it goes in combination with the .IC, which is the initial conditions node by node. If you leave it by default, it gets it to 0, and it puts the circuit in a way that is different, that you can see the results, and it help you either converge or get the right results. Now, we just put a suggested set of values, and I have to say here, there's no real bulletproof answer. It's all, if you don't know that the circuit's dependency to your parameters, then it's very dangerous. So you actually have to always understand the impact of these things, of these parameters, whatever you change, on the solution. And if there is a significant converge versus not converge is a very clear issue. But if you have changes in the values of the voltage reference, for example, based on some of these, that is, it's either an indication of the multi-operating point situations, or you actually have a bigger problem in the circuit. So, and I apologize just because we're here, it's a lot of text, but it's the best way to do it is to, without getting into the mathematics of every algorithm, is to actually just walk through them and then demonstrate some examples. So I just wanted to check first if there is any questions at this point.
If I can interject a comment here, just to mention that Reltol is the option that I have been playing around with in the newest test benches that I had everybody download for the challenge, so that if you can find a way, if you're having problems getting a circuit to converge in the ACE, the characterization tool results, that if you can figure out a change to reltol that makes it work, that's the easiest for us to work with, I guess. If you remember, I mentioned that if you submitted it and the remote ACE was continuing to say that something was failing because it wouldn't converge, that I would allow the challenge to be submitted with the error as long as you had a simulation to show that it does pass. So if you can make it pass with a particular value of reltol, then it's very easy for me to go and tweak the test bench to add that value of reltol that works. So that would be my recommendation for the first attempt to get something to converge, is use reltol. And after that, I guess what would be the order of things to try? I guess reltol first, ITL 1 second, maybe abstol, then gmin. I would leave rshunt for the very last because of its effect on the actual circuit topology. Does that sound about right, Mohammed?
Yeah, and actually that's important. Actually, one of the things I should do here is that ordering is important, because if you're trying multiple things, so I tended just to add them here as a recipe that I just put to thinking that I can maximize the impact, but it's true. Reltol, ITL, abstol, gmin, and then the rshunt is really where you're really modifying the circuit. That is something that you don't want to do in general. So you should keep it to the last, and it depends on also what type of analysis and circuit that you're talking about. So I'm gonna actually, I'm depending on a lot of references here, looking at the whole multi-operating point issues, and how you at least understand it or detect it in some way and approach the problem, approach the understanding of this. And I just followed some of the that exist, just because it's actually very nicely done in examples like when you
Mohammed?
Yes.
Just a question before you proceed. Based on what you just explained, let's say I figure out a set of values for the tolerances and do a .dc, and it works, but the same values don't work when I do a .dc with the temperature sweep. So do you have like some suggestion to get a .dc with the temperature sweep working compared to just a simple .dc?
So to be honest, the answer here is, so I'll tell you what I would do, and that's what if I did an experiment on these parameters separately, because what happens is when you change the temperature, you're changing some of the values in the equations in a way that again will create a different it shifts the matrix in a certain direction. So it depends on the change in the temperature, how far it is, and if it is from 27 to 125, then that's a big change, and it tends to be different. So I tried, in this case, actually, I tried several values in a linear way that would get me the solution. Now, they could be different, which is not desired, okay? Yeah, but the right approach is to find one that works for both through the trial and error, guided by by certain boundaries. Like for example, you never put the reltol 1e minus 2. I'll tell you through the experiments you run, it's going to change. It's going to basically cause you to get bad results. So there are guides that you don't go higher than a certain value for reltol, or for example. So I don't, again, it's not very, it's not very, it's not surgical. It's not every circuit has, I'm sorry, it is surgical. You'd have to make a judgment. And the key part of that is that you use the parameters in the order that, something like what Tim mentioned, that don't impact the circuit performance. So I don't know if I successfully made you any more comfortable, but it is what I did. I always have doubt about the solution, so I do experiments. With one goal is to ensure that to get this circuit to converge and also correlate the values and confirm that the final answer does not change or not sensitive to the variation in the tweaks or the sensitivity. Actually, obviously everything is sensitive, but the sensitivity in the variable in the performance I'm measuring, whether it's like could be noise, it could be something transient response or whatever, it should be low to these parameters in terms of change, or lower than what I'm looking for the system spec. So if the system spec is within a certain range, sometimes it's very tight, then you can't have an error tolerance that's high. And obviously, if you get to that, that means there's the circuit is very sensitive, or architecture being used is very sensitive anyway.
Okay, thank you.
So all what I'm going to say here is that if you feel that there is something that is a case that is not responding, or you see some anomaly, this is something we would be happy to look at it specifically, and find work around it.
Okay.
Yeah.
Yeah. Thanks.
So I'll have to say here that I actually borrowed some of the things that I found very nicely done in some of the PhD thesis that I will actually put it out on there as part of the references. But that's an example of a circuit that would have multiple operating points, and it's actually almost looking at it, you will have to treat it the way you treat when you're doing AC analysis, or like frequency response or system analysis of your circuit for stability and things like that. But this is not a stability issue. It's more of the similar things where you do sensitivities. Like here, you look at the nodes here, what they're doing here, and they're saying that between node 1 and 3, there is a feedback loop where if node 1 changes by a certain, it's a negative feedback. So when you change it, your node 3 is going to respond negatively, and there's a loop here that is closed. And the approach to actually understand the operating point, one of them actually, and that works the most, is to understand where the circuit can, if you're to do some sort of artificial sweep. So in this case, breaking the loop, the feedback loop in here, and applying that signal directly to that artificial input and see what is the return. And obviously, a valid point where you have a solution where they intersect. And one of the things that I've done, and this is actually I'm going to go here. I have this is a very crude, and it's not actually even on this process, but it's a very crude circuit with similar performance, similar characteristics, and it has and basically it has a startup circuit that will move the circuit to speed fast to the point we want. But I wanted to show here that this was actually again it's a current mirror in a certain way. I broke the loop here, and I put and I set it up in a way that is I can sweep that point and see the impact of the the simulation of the just and the sweep here, I'm not doing it in a DC mode. I'm doing it in a transient mode. And if you look at the sweeps, unfortunately, it's all coming green, which is not something green and green. So let's just remove for now. But you'll see here, these are the 2 points that are in the circuit I was looking at here. As I'm sweeping one of them, there are multiple crossovers. And these multiple crossovers mean that they are valid, they are mathematically valid potential operating points where these 2 nodes, if I'm sweeping one of this one here in a linear way, as the circuit behaves, or I'm sorry, responds to that sweep of voltage here, the other node that is in a real scenario it's just the same. It's connected. You'd be able to see the response in a way that you can. There is a crossover. Then there are multiple points. Multiple reporting points, and that is very sensitive to temperature. So if you try such an approach and you change the temperature, it depends on the circuit, obviously, but that will change with temperature, and you have to understand that if the circuit has multiple of these points, the startup circuit's job is to put it in the right point that you want. And that's actually why we need startup circuit in this case, is to snatch it into points that we design for. Back to something like this, there is another example that was used with actually a different approach where multiple loops were used, where if you're using high gain stage to control the accuracy of the voltages across the mirror here and the transistors here, so you will have multiple loops, and this is like just looking at it. You're going to have a loop here and a loop here. You can actually looking at breaking the loop also is going to be interesting, which one to break and which one, if you have more than one loop in the same direction, which one is dominant. So again, they're using here in that graph, which is basically between node 1 and node 3, there are negative feedbacks. Between node 2 and node 3, there's a positive feedback effect as well. So you can do multiple types of breaking the node, the loop. And now the word loop here that applies to the different which loop. So in a case like what the cases that we were talking about, so now breaking this loop here, you can break it this way, and again study the behavior in one way, or break it from a different place. This is breaking actually the 2 loops. If I look back on the circuit here, if I cut the value, the output of the amplifier, I'm breaking the 2 loops altogether. If I'm breaking only the gate of this transistors, I'm breaking 1 loop. So depending on these there's no bullet, or single answer for that, but there are rules, and I learned that from one of my colleagues here also, because which loop do you choose to break, and it depends also on this the mathematical accuracy that you want. Usually if you try to break it from in a place where you can inject a lower, the next stage would be a lower gain, so that the sensitivity is low, so you don't have to apply very small numbers for the sweeps, and you'll be able to reach accuracy. So now if you see something like this, you'll see the blue here is actually representing of the sweep being swept. It's the 45-degree line, and then you will see, depending on where you break the loop, you will see different responses. But in all cases, you'll find that there's an indication of the multiple operating points, and the design of the startup circuit needs to be in such a way to bring you to the right point that is intended for your design. And the second one is that the behavior of the circuit around the given operating point, it needs to be stable, or if it's not stable for a around a given operating point, it will get out of that state. So, and obviously that's not. But if it is stable, it's going to give you a bad solution. Like for the reference value, to give you a point, like a lower value, valid, and it gets stuck with it without a startup circuit. So, if it is, and again, I'm not giving a very specific case, and I think actually one of the things we want to elaborate is to actually get into a real, real depth on how to do it in different ways. And just for the sake of giving you something to work with, I've done what I usually do, which is basically finding references that are very nicely done about the descriptions of these problems. And then you'll find that what I just described is, they call it the continuation methods, where, and they applied in different, this article on the left here, they have multiple called groups of recipes to tell you what you do. And then I included some of the articles that related to the bandgap design and how, just in general, the design of the startup circuits and working with. Now, the one of the articles that are really good, or the one that I presented parts of it, is this one, and it's actually that's a paper from PhD thesis, around the PhD thesis, and they're actually talking about breaking the loop multiple ways. They're doing either current feedback or voltage feedback, breaking it or not. So, and I recommend, I have them on the website, and I recommend that you dig deep into them and replicate these experiments in a way that enables you to understand the circuit. And I think this should be a general practice for in general. So I'm sorry, I think I took the full hour, but I'd like to just pause for a second here, see if there are any questions. And I understand it's a bit theoretical versus the previous versions, but it is in a big degree intended to just educate you to where you learn more about how to handle the circuits. Are there any questions?
Hello?
Yes. Yes.
Can you hear me? I'm sorry, I just joined, but I have a question.
Go ahead, please.
Whenever I use RW resistor in my transient simulation, they just don't complete.
Say again. Could you repeat it? I didn't hear that.
Can you hear me now?
Yeah. When you mentioned question, there was a noise of that.
I want to use RW resistor in my design.
Yes. Okay.
But whenever I place this resistor in my simulation, my transient simulations won't run.
And is it okay, like the convergence problem, or is it
It just don't give me any error, but the initial transient simulation shows me NAN.
Okay. I'd like to take a look at that. Would you be able to? May I ask who is it, Naveed?
Yes, Naveed.
We actually I'd like to take a quick look at it.
Sorry, I cannot understand you.
Yeah, sorry, Mohammed, you're getting muted out. But if you can hear me, I think that's. Sorry, Naveed, can you mute while I'm responding, because I'm getting a lot of background noise from you. Okay, thanks. Sorry. Yes. Yeah, so if you can issue a help desk ticket, that would be helpful. So I don't know exactly what's going on. I know other people have used RW resistors without problems. So we can take care of that through a help desk ticket.
Okay, thank you.
Sure.
Okay. Well, and that's about it. And then if please, if you have any questions or even more details, we can go deeper. And then also we can if there are specifics related to your circuits, we can help. In this case, file a help desk ticket. And if there are things related to general theory, we're going to have a different, deeper theory coverage later, maybe after the challenge. But I think it's worth actually doing some of these things in a deeper way.
Can I ask?
Yeah, please.
I'm sorry, but it's not directly connected to this topic, but it might also be, I'm not sure. It concerns the results the characterization tool gives back. I just have a question. For example, at one of the three combinations, it tells me pass,
Mm-hmm.
three values. But it says, in brackets, it says 1.16, which is the value we should have. And I do have it in my own simulation. But here it says that it passed, and it gives value of 3.4 minus fifths.